Good morning. So this is a question and answer um, session in response to a question that I received a couple of days ago by some of you, and concerns theories in which you have also uh, odd coupling. For instance, and specifically a third order coupling in four dimensions. Well, why should we care about these theories? Well, first of all, because they are um, you can think about it. So, in our statistical field theory description, we sort of discarded terms with this structure when studying the ferromagnetic phase transition because we use the argument it would violate the reflection symmetry. But in general, there are other field theories that you can use, which refer to different physical systems in which such symmetry may not apply. Specifically, this Hamiltonian in four dimensions doesn't have a direct physical interpretation of a statistical system, say a spin system, because spin system exists up to three dimensions in real life. But for instance, it represents, and I'm going to change this now, the Euclidean action, the imaginary time action of a scalar field, which represents a spin zero point chargeless particle. Well, if you're not interested in statistical field theory, in quantum field theory, you just consider this as uh, one possible, uh, one possible Hamiltonian that you might consider for some physical system you're not particularly interested in. So, like an exercise, a conceptual problem. If you come from a quantum field theory point of view, then this is a natural quantity to consider because it's expressed the imaginary time action of the Klein-Gordon chargeless field. Now, so the point of the student is that in four dimensions, this term is relevant and this term is marginal. So you would imagine that if I run under renormalization group flow, I can discard this term and retain all of this. However, if I do so, I have a theory in which the largest term is an odd power, which in one dimension, just as a cartoon, would lead to an energy profile, an energy that is not bounded from below. And this does not represent a physical theory. For a Hamiltonian or a Euclidean action to represent a physical theory, it must be bounded from below. Otherwise, the system naturally evolves to minus infinity as a minimum energy configuration, which of course doesn't represent any physical system. So the question of the student, if I interpret it well, is, well, how is it possible that under renormalization group flow of this theory, I make a theory that is viable, because it's a phi to the fourth term, into a theory that is not physically viable? And the answer is, well, I had to think about it a little bit because what I'm giving is my personal answer. I must say I never encountered this question before. So, but I think I have my answer in my mind, and I think it's interesting to look at what happens into this theory. Let me neglect for a moment the incriminated term, leave it aside for 1 second and come back to that and look at this theory in four dimensions. Now, if you look in Pesky and Schroeder and you do all the calculation, you discover that this marginal term, this is the relevant term, and this is marginal. And if you do the quantum field theory calculations of this, you discover that in the perturbative regime, this coupling runs towards the fixed point of zero coupling, which means that phi to the fourth is a trivial theory. Because if I start in the vicinity of the, so suppose I have two parameters, of course this is a renormalizable theory, so I won't generate, well, let me not say things that are not strictly true. So I have a space of parameters. One of these parameters is my, in our notes, let me call this provisorily lambda because in Peskin-Schroeder I believe it's called lambda. And I have my mass parameter. Here I have lambda, and here I have C and D. I can imagine more dimension. If I don't know if you have taken Pagani's course in analytic mechanics. Pagani likes to draw multidimensional spaces, like three-dimensional spaces with many arrows, and that's what I basically am cartoon-wise representing in this picture. But there's a bunch of parameters here. But let me not worry about the other parameters. They are all irrelevant, so they all flow to zero. That means that if you start from here, these parameters, C, D, and whatever, they run towards zero. But also lambda, the lambda parameter that is marginal, also logarithmically runs to zero. On the other hand, M is relevant, so it grows. Which means that RG flow of this theory is towards a theory with a much larger mass and much smaller coupling, right? So basically, you can make by RG put in the same universality classes a theory that is for all practical purposes a free theory, but very massive, and put it in the same which sits here, so to say, and put it in the same equivalent classes of the theory that you started with, which means the lambda to the fourth is basically a trivial theory. Does this now, if I now put I restore my original notation, I put a lambda phi to the third phi 3 and a u naught here. Now this becomes u naught, and go back to the question that the student was asking. So now I put a lambda here. Now what happens is that lambda is marginal, is relevant in phi to the fourth. So basically I'm going to a theory, I'm running towards the configurations in which I basically, under G, I stick to this plane, the mass square and lambda, starting from outside the plane. You see what I mean? So basically, I start from a point that has a finite distance, because I have a finite u naught, from the plane selected by m squared, m lambda. And as I run under renormalization group, I approach this plane and get far and far from the origin. So the question of the student is, then at some point I can neglect this, and then I have an unstable physical theory. Well, that's, according to my view, this is not true, because what are you running to is to run towards a system in which u naught is arbitrarily small but finite. So now if you take a polynomial p of x, which is, say, a x cubed plus b x4, and you take b as small as you want, but finite. So say let's take b 0, 0, 0, 0, 0, 0, 1. So typically what will happen is that your polynomial will take a structure that is going to be like, but very, very, very far away from the origin. Eventually, even though the coupling is very small, this will take over. Because no matter how small this coefficient is, this term, this is one of the fundamentals of first-year calculus, right, will eventually take over. So this will mean that the vacuum will be shifted towards a finite field configuration. So if you translate this into this problem, I guess you will get a non-trivial vacuum. A non-trivial vacuum is one in which this is different from zero. But non-trivial vacuum are difficult to treat perturbatively. You have to treat perturbation theory around the vacuum. So all these arguments probably get even more complicated in the presence of a non-trivial vacuum. So at that point, I don't know if this RG arguments that are done in perturbation theory still apply to the non-trivial vacuum. So, but at least I want to say the quote quote naive argument, we cannot neglect this, and again in physical theory, I think it's a bit too naive to be applicable, and I think the the general framework of field theory is still safe. Thank you. I hope I answered the question.